Good evening, everyone. I am Mr. Ish. Thank you for joining me for this simple video here, simple topic, average value of a function. When you're talking about, in general terms, the average or the mean, you have a certain numerator, you have a certain denominator, you have the sum of all the values in terms of your samples, whatever they represent, you sum them all up and then you divide them by the total number of values, your n values, and that gives you your simple average, your simple mean. But that represents a situation where you have a finite values with regards to a finite interval. Everything we're looking at with that simple average, simple mean is all finite. But there are situations where you may have a very well finite interval, but within that interval, you can have infinite number of possibilities or measurements or readings that can come about. And then in that instance, you're thinking about doing an average of an integral. And this formula comes about. You're doing an average of a function with 1 over b minus a. These are your upper and lower limits. And then you do your definite integration procedure. The average value of a function is very useful in you being able to do an average in terms of real life models of something within a finite interval, but for which you can have an infinite number of measurements come about in that finite interval. Very quickly, just the application of this. If you have a function which is f of x is equal to x squared and you have to find its average, what's the average of this function over 0, 2? It's not hard, you just plug everything right here. These items here must be within the domain of this. You're looking at something which is 1 over b minus a, which is 1 over 2 minus 0. You're looking from 0 to 2. You're looking here at your f of x dx. But your f of x here is the quadratic x squared and you can plug that in. When you integrate this, you have 1 over 2, which is from right here, this 1 over b minus a. You have an x cubed over 3 and then you're doing from 2 to 0. 0 is meaningless, but you have 1 over 2 times 8 over 3 and you end up having 8 over 6 and you have 4 over 3. So the average of this function, whatever it might represent in terms of a model or an experiment with regards to its values which are being inputted, over this interval, the average of all those possible values that can come about from this experiment over this lower and upper limit would always have this value as their average, 4 over 3. In a nutshell, you can read it as that. Very quickly, let's look at another application. Suppose you have a specific function sine x and you're looking at everything here from, let's say, 0 to pi over 2. This sine x represents some sort of model. It represents some sort of real life phenomenon, and these are the lower and the upper limits of that finite interval. Readings can be obtained from the start and from the end, and all those readings, when you would average them out, what would the average of those readings be? That's what we're talking about, average value of a function, and that exactly would require you to use a formula such as this, 1 over pi over 2, right? 1 over pi over 2 minus 0 is 1 over pi over 2. You would do all of this in terms of its definite integration. Here you get a 2 over pi, and then you do the definite integration, which would be minus cosine x, and you're looking here everything from pi over 2 and 0. The actual placement of these intervals in the antiderivative, you can push this minus outside if you want, minus 2 over pi. Then you're looking at cosine x from pi over 2 to 0. You have a minus 2 over pi. Cosine of pi over 2, 90 is a 0, but cosine of 0 is a 1. And then you end up having 2 over pi. You can do a calculator decimal value of 2 over pi, but you don't have to. If this sine x represented a real life experiment, a model, and your start value and your end value, or in terms of your start of your interval or your end of your interval, all the possible values you could obtain in that experiment, and you would compute them using this model, the average of all of those possible values would be 2 over pi. Let's look at this actual practical question here. It's adapted and modified from a question from one of my calculus textbooks, and I've modified it slightly for this presentation. This will be our last question here we will look at for this video. We have a time interval provided here from 7 a.m. to 7 p.m. We have a certain function f of c, 50 plus 14 sine pi c over 12. It represents a temperature function for that specific city, which can be utilized to measure a temperature at a given point in time. If we are asked that over this window, 7 a.m. to 7 p.m., which is a 12-hour window, what at any given point in that same interval would be the average temperature of this specific city? Well, we know we're looking here from 7 a.m. to 7 p.m. We're looking here at a 12-hour window, and we are looking here at a concept of average value of a function. Our basic premise here is we have to determine the average temperature. How can we go about doing that? We know what the formula is. We need to find what the interval is. This certainly is not my interval. This only represents the start and the end point of what could be an interval. but it represents what is really a 12-hour window. Our interval would really be from 0 up to 12. Why is it not from -7 to 7? Because you cannot really convert this into x-axis coordinates in the true form of the sense, but it can represent a certain window or a period of time from which you can measure from 0 to when it ends, 0 to 12. This here is indeed our interval. It'll be 1 over 12. As you know, 1 over b minus a, you're looking here from lower limit 0 up to 12, and this entire function has to be integrated over this limit. 50 plus 14 sine pi c over 12, and here the independent variable or variable is c here being representing degrees Celsius for all that matters. From this step it's easy. You just want to separate everything into their own independent integrals across the positive. Nothing wrong with doing that. We have 1 over 12, 0 to 12, we have a 50 dc. Then we have a 1 over 12, and then we have 12, 0, we have 14 sine pi c over 12 dc. If you want, you can push this out, the 14, you can. I can push the 50 out. I'm getting a 50 over 12, and then I'm doing the antiderivative of this would be a c, and then I'm doing 12 to 0. I'm just working right here on this part, and then I'll set it aside. 12 comes in, 0 comes in, 12 is multiplying with 50 divided by 12. The 12s will cancel out. From all of this, you'll just end up with 50. But you know, 50, all of this here representing temperature, it would really be 50 degrees Celsius. But this part right here, in terms of definite integration, gives me a 50. That was easy. Now we'll worry about this. We can do a substitution here. If u is equal to pi c divided by 12, then du is equal to pi over 12 dc, and then dc is equal to 12 over pi du. We have to change our intervals. This is c1, this is c2, so we have to do u1, u2 with regards to this. When 0 comes in here, you get a 0. When 12 comes in here, you get a 12 pi divided by 12, you just get a pi. So that's not too hard. With all of this substitution, now let's actually work over here. We have a 1 over 12, and we have this new intervals. We have pi, and we have a 0. We have a 14 sine u, and then du is attached with the 12 over pi, right? 12 over pi du. See, 12 over pi du. This 12 can cancel out with this 12. And then what we really end up having coming out is a 14 divided by pi, and we can clean up all of this. We'll have a 14 here, we'll have a pi here. We can remove this, and we've already taken care of the 12, and all of this can be rewritten as just sine u du. So we just have to integrate this, and we have this 50 already integrated, so it's not hard. Let's work only on this part right here. We have a 14 over pi. The antiderivative of sine u is a minus cosine u. We're looking at everything from pi and a 0. This minus can very well be brought right outside here, and there's absolutely nothing wrong with doing that. You bring in the pi and the 0. When you do cosine of pi, you have a minus 1. Then you do the difference of the two. When you do cosine of 0, you have a 1. Minus 1 is a minus 2, right? Minus 1 is a minus 2. And then you have this minus 14 over pi sitting over here. When you multiply all of this, you're getting a 28 over pi. This 28 over pi is coming from this integral right here, this definite integral. So why don't we erase all of this and bring it right here after the 50, the 28 over pi. 28 over pi represents a good finite value here, coming from the second part of this entire integral from right here. And then, you know, we can do a good calculator answer. We'll do 50 plus 28 over pi. 50 plus 28 divided by pi, I get 58.9. Why don't I round that up to 59? We have 58.9 degrees Celsius, but we'll round it up to 59 degrees Celsius. What does this 59 degrees Celsius mean? Well, it's a value obtained from this temperature model over this entire 12-hour interval for this particular city. This right here represents the average temperature of that specific city over this time period. If someone were to ask you from 7 a.m. to 7 p.m. if you had these infinite number of recordings coming in, what would be the average of all of those recordings? Well, it would be 58.9, or you can just say 59 degrees Celsius. So this model here in terms of application is an excellent example of average value of a function, how over a very finite interval you can plug in an infinite possible number of readings and then get a good finite value in terms of an average. That average would indicate the average of all of those values coming in, and you could read that out as a good value. Well, that's it for this video. Thank you for watching. Have a nice day.